Good afternoon. So we're going to talk about implementing pipelines, and there are going to be two lectures on this. So today I'll be talking more about how to implement various modules that are needed to implement pipelines, and then in the next lecture we'll be talking about the actual processor pipelines. So next lecture is the one that will directly be beneficial to you for doing your project. But unfortunately, the next lecture will not be held this Thursday, it will be held the following Tuesday, because this Thursday we'll be doing synchronization, which is also an important topic, and we need to do it because that's also going to be on the quiz. While the pipelining stuff is mostly for the project, there might be questions on pipelining in the quiz also. All right, so let's begin with this. What you have seen is some general ideas about pipelining, as well as some specific solutions for processor pipelines. So I'm assuming you will remember all that. You will know something about control hazards and data hazards and how these things can be resolved by using epochs, etc. And what we'll be doing in today's lecture and the next lecture is how do we actually design hardware to do all that. So just like in the previous lecture, I will first focus on some modules like Fifo, register files, scoreboard, etc. needed to implement these pipelines. And the main thing in today's lecture is I'll be introducing a new element called EHR. EHR stands for Ephemeral History Register. So it's a generalization of a register, or it's a particular type of a register, and once you use that, then the power of the kind of designs you can write goes up significantly, and you can do certain things with it, which I'll be showing you. All right, so let's revisit our inelastic pipeline. So recall inelastic pipeline was that we are separating stages by registers, and everything moves synchronously. So in that sense, it's inelastic, right? Because everything moves at the same time. And if you write the code for this, you can see it looks pretty straightforward. That in the synchronous pipeline, you will move things from the input queue to register 1, from register 1 to register 2, from register 2 to the output queue. So those are the actions represented here, and once you have done that, then you can dequeue whatever was in the input queue. And of course, everything is happening in parallel, so the fact that I wrote inqueue.dequeue first doesn't matter, right? Because all the actions will happen simultaneously that are shown in this, just as all the tokens moved simultaneously in this. So just to refresh our understanding of how things work, when can this rule fire? When can this rule fire? What is the guard for this rule? Yep. Very good. So this rule can fire only when there is something in the input queue and the output queue is not full, because it's all synchronous. It moves like this. So there has to be something here and there has to be space there. That is the control flow. I mean, if you're going to use this pipeline, you will be imagining something like this, right? And that's input queue has something, output queue has space. And as I said, atomicity, all the registers, all the actions on the queues will happen simultaneously, right? In one shot, one clock cycle. Okay. Now it turns out this control flow is not quite correct. And you say, why is it not correct, right? It's not a proper control flow. See what will happen. Suppose you get to a stage when there are two tokens sitting over there and nothing comes in the input queue. Do you expect to drain out these two tokens from the pipeline? Right? So, regardless of whether something is in the input queue or not, you can't leave tokens in the pipeline. I mean, that will make no sense, right? Similarly, to start this pipeline, right, must leave. And similarly, you can say, if there is no token in stage 2, in some sense, then nothing should be enqueued. You don't enqueue holes or something in the output queue, because these queues represent something. So in other words, to have proper control, you must deal with the fact that this pipeline will sometimes start and sometimes stop, or may have gaps in inputs. You may not get one input every cycle or something like that. So that's a much more realistic view of the world. And the question is, can we modify this rule to deal with all these things? So that's the first thing, that simple looking rule doesn't quite capture the reality. I mean, if you were to build real hardware, it'll be more complicated than that. And the way we do it is we can introduce the notion of a valid bit with the registers. We can say whether this register contains something or not. So that's the valid bit associated with it. And now I can write a rule that says, as long as input queue is not empty, you can take something from the input queue and dequeue it, right? Put it in sreg1, and at the same time mark its valid bit to be valid or true, depending upon what type you use for it. And if there is nothing in the input queue, then you can mark the valid bit as invalid. There is nothing in it. So this is just keeping track of every time I'm taking some action. If there is something, I do something, and if there is not, then I do something else. All right? In the middle stage, it doesn't matter whether there is something or not. I can just keep moving things from left to right, left to right. I don't even look at the valid flag. I could have been slightly more particular and said, if it's not valid, just don't do anything and just put, but it doesn't matter, because in combinational circuits, if you're taking something and this output is not going out anywhere yet. Okay, very good. And finally, what do you do? If there is something valid in the second register, then you want to enqueue it. It automatically means that if there is nothing valid in it, you don't enqueue anything in it. And when you look at this, it will take you a few minutes to derive the guard for this, right? What is the guard for, this rule? And it's complicated, right? Because guard will depend upon whether the valid bit of the second register is true or false. You'll do something accordingly. But BlueSpec will take care of it. But you, as who's learning all this stuff, must try to argue it out with yourself. What is the guard for this? Okay. sreg1 and sreg2 with valid bits are beginning to look like a one-element Fifo. Right? What did one-element Fifo have? It had a register and it had a valid bit. And then there was some protocol on top of it, when things should move and when things shouldn't move. So why don't we use, Fifos for this? And if we do that, our life gets dramatically simpler. Now you will have to agree with me that this code is trivial to write. Pick something from the input queue, put it out in the output queue. And there are 3 stages, so there are 3 such rules. Each rule is pretty straightforward to write. And furthermore, the firing condition for each rule is also very easy. If there is something in the input queue and if there is space in the output queue, just that rule can go at that point. But surprisingly, this nice looking picture creates a new problem for us. And the new problem for us is these rules are easy to write, but introduce a new concern, which is these rules can execute concurrently only if your queue is such, your FIFO is such that you can concurrently NQ and DQ from it. First of all, does everybody agree with me that if you have these three rules and they cannot fire concurrently, it's a lousy pipeline, right? I mean, the whole idea was that we want to do many things in parallel. We want many things to happen simultaneously. So this is not just a desire. I mean, this is the essential characteristic of the pipeline. Otherwise, you are throwing the baby out with the bathwater, right? We do all this effort and then we discover it doesn't run properly, right? It runs only one stage at a time. The whole goal is to run 3 stages in parallel. So the rule suggests it can, provided you have the right kind of FIFO. You have a FIFO where you can do NQ and DQ simultaneously, right? And I will do this again, but if you look at our one element FIFO that we had designed, forget about executing NQ and DQ concurrently. They are not even ready at the same time. Because in one element FIFO, either it was empty or it was full. It could not be simultaneously empty or full. This is very problematic. So, and that is captured here in this conflict matrix for the FIFO, where ME stands for mutual exclusion, that these two things can't happen at the same time. So this FIFO was easy to write, these rules were easy to write, but unfortunately when you try to use this FIFO to build this pipeline, we got nowhere, so there is no pipelining. Very troubling. Okay, so this is something to remember, that we need the right kind of FIFO for this to fly. Okay, let's quickly re-examine the FIFO, one element FIFO we had seen earlier, right? So you had all these NQ and DQ actions and first init, and this was the conflict matrix which you can derive. NQ conflicts with itself and DQ conflicts with itself, and first doesn't conflict, you can be looking at 2 firsts at the same time. But as you can see from the conditions for NQ and DQ are mutually exclusive. One is V, the other one is not V. So they cannot happen together. That's how we derive this. And when DQ and first happen together, then it behaves as if first happened and then DQ happened, which is what you want. I mean, you were looking at it simultaneously, so you want to take it out and then you want to take out something and then DQ it. Good. Now, can we make a FIFO where NQ and DQ can be done simultaneously? How many of you say yes? Yeah. 2-element FIFO. All right, let's go to 2-element FIFO. So I have my 2-element FIFO, and each element has a valid bit associated with it. And just to make the design simpler, I mean, of course, initially it's all empty, but we will assume that if there is only one element in the FIFO, it will always sit in DA. Okay, so we will justify to the right. If there is only one element in this FIFO, it will be in the right hand side. Are the rules clear? I mean, what we are trying to do here? All right. So first, NQ will store the data in DA and mark VA is valid, right? And NQ can be done as long as VB is false. Okay. I think I made a mistake here. First NQ will store the data in, first NQ, right? FIFO was empty to start out with, right? NQ can be done as long as VB is false, and DQ can be done as long as VA is true. That's the kind of FIFO we want to write. All right, assume if there is only one element, then it sits in DI. So this is not difficult to write. Let's just quickly write down this code, right? Does this make sense? The NQ operation. As long as there is nothing in the first element, right, the VB is false, then you are storing the data in DB and marking VB to be true. And similarly, you can write DQ. As long as there is something in DQ, you can take it out and mark it false. And first will be very similar too. As long as there is something in VA, you can read it. So far, so good. But the problem is if you just did this much, and this looks good, right? Because I can do NQ and DQ in parallel. But what will happen, we started out with an empty FIFO. You do an NQ in it. Where will NQ be sitting? Where will the data be sitting? It will be sitting in DB. But in the canonical form, we want it to be on the right hand side. Why? Because otherwise you can't DQ it. Because DQ is only checking the flag in the DA place. So yes, you are successful in NQing, but you have to move it here in order for DQ to work properly. And you can imagine that while this token is in DA, at that time you can do a DQ as well as you can do an NQ. So this will be empty, this will be full. So yes, progress. But the question is, this token has to be moved from DB to DA. And for that, I write a separate rule. I call this rule canonicalize. And what does that rule say? That as long as there is something in DB and nothing in A, then you must move this token here. That's all it does. So it brings it into the position where these rules can execute again. So for about 30 seconds, I'm very pleased when I write this code and I'm saying, wow, you solved the problem, NQ and DQ can happen together. And now I draw the conflict matrix. Indeed, it looks like this, you know. But remember, there's a rule inside too, so you have to see what it conflicts with. And you find that that rule is actually mutually exclusive with NQ, DQ for everything. So you say, what's going on here? I can do NQ and DQ, and then the whole thing sort of goes comatose, or at least it looks like that from outside. Nothing can happen. I can't NQ or DQ until it makes an internal step of canonicalization, until that token is moved from left to right. Such designs are known as having dead cycles. That you did something and you are unable to do the next thing. There is a forced dead cycle upon you, right? So effectively NQ and DQ, even though you did them simultaneously, it wouldn't have mattered, right? I mean, you could have done them because you are introducing an extra cycle anyway. So, right? And canonicalized rule introduces a dead cycle after an NQ and DQ. So we tried our two-element FIFO. That didn't quite solve the problem. It got part of the way to the solution. All right, so let's think about it a little bit more. What can we do? And before you go too far into it, let me just tell you something, okay? You shouldn't be knocking your head against the wall, because what we are trying to do is impossible. in the blue spec we have seen so far. Okay, in blue spec one thinks of bypassing in terms of reducing the number of cycles it takes to execute two conflicting rules, right? So two mutually exclusive rules or two conflicting rules, we say we can't do them, so we'll do them one by one, because that's the semantics, one rule at a time semantics. Okay, so an example, design a FIFO where a rule performs an NQ on a full FIFO provided another rule performs a DQ simultaneously. Now I'm changing the rules of the game. I'm saying I want you to design me a new FIFO, right? Where NQ and DQ can go on in parallel provided DQ was happening. If DQ was happening, then you can NQ. If DQ was not happening, then you can't NQ. So you are bringing into account something new. Nobody says this is happening in the same rule. Another rule is trying to DQ, and this rule is trying to NQ. You say, if you execute these two rules together, then we are fine. We have a FIFO where we can say, okay, NQ and DQ are happening simultaneously. All right, it requires signaling from DQ to NQ. Somehow you have to say a DQ is happening right now. So this NQ will be okay. Consider another situation. Let's quickly look at this rule. RA rule says X gets Y plus 1, and rule RB says Y gets X plus 2. So this is the classic example of cycles. They're looking at each other, they conflict, right? You can't order them, so they have to be done one by one. And you can ask the same question, what can I do so that I can actually execute these rules in parallel? So that I can execute these rules simultaneously, right? Can I somehow pass the value of X from this rule to the next rule? Because if I could, then I can say, yeah, I can execute them in parallel. But I don't know how to do that, right? There is no way I have shown you to pass values from one rule to another rule in the same cycle. Of course, the value can be passed in the next cycle. But by concurrent execution, what we mean is we want this to happen right now, right? Simultaneously. It requires communicating the value of X from RA to RB in the same cycle. And this is not possible. None of this is possible in the blue spec you have seen so far. So that's what I want to tell you about. So limitations of registers. That's all you have seen so far, registers. And the limitations are that two methods cannot communicate with each other. A rule and a method can't communicate with each other. Two rules can't communicate with each other in the same cycle. They can always communicate. You go and set something, the rule will see it in the next cycle. But what we are trying to do here is to do it in the same cycle. We want to increase the concurrency. We want to take away this wasted cycle. Wasted is not the right word, but if we can reduce the number of cycles, it will be fantastic. That's the goal. Okay, EHRs to rescue for this, and let's understand how ephemeral history registers work. Do you recognize this picture? This is the picture we started out with in our first sequential. Forget about the lower ports in this. The upper port is simply the D flip-flop we had introduced in the beginning, that there is a register, where if you enable it, then it takes the new input that is coming in. Otherwise, it just keeps using the same input that was already in the register. Right, so this is the picture you saw in the first lecture on sequential circuits, sequential machines. Okay, so I'm going to add something to it and call it EHR. So what am I going to add? So first thing I'm going to add is, and if you do it like this, by the way, then it's like saying read happens before write, which is how you have been dealing with it. Given a register, if you do read and write simultaneously, you see the old value, and whatever you write in it will only be visible in the next cycle, afterwards. So now what I want to do is enhance it and give you another port. So either you can see the old value, or you can see the new value, incoming value, into the register. This is a bypass path. So here I'm giving you a register with one write port and two read ports. Read port R0 reads the old value in the register, R1 reads the new incoming value. If there is no incoming value, then R1 will also read the old value. Is this picture clear to everyone? I have created a bypass from input to output. This is a combinational path, right? This did not exist in your original register. In the original register, you had to enter this yellow body, the D flip-flop inside it. But now there is a combinational path along this bypass that you are seeing. Everybody understands this? Such a register is, trivial to build. But I also want to deal with the case that there may be another write coming in at the same time. Right? So I want to give priority. If there are two writes into this register, I want to, instead of treating it as an error, I want to say the second one has priority over the first one. And if you want to understand hardware-wise what it will look like, so if, by the way, bypass behaves as if read one happened before the write took place in this. All right. So instead of feeding directly, incoming data, what I'm saying now is that the output of it, let's look at the second write coming in there also, and if that is also enabled, so somebody tell me what will be, what is going in here if both the writes are disabled. If both the writes are false, yes? The original one? Yeah, good. And what will happen if one is true, write one is true, but the write 0 is true, but write 1 is false? And what about if write 2 is true and write 1 is false? Look at the diagram. So suppose this thing is true, but this thing is false. So old value will come here, right? P value is coming here, and this is true, so therefore you will get this value going in here. And if both of them were true, then you will definitely get the second one. This is a pretty simple hardware structure, right? But I don't want you to be thinking about this hardware structure all the time. We'll just treat it as a register with two read ports and two write ports. I call it ephemeral history register because it's letting you look a little bit in the history even though there is only one register out there. EHRs is the primary way of introducing bypasses, increasing channels of communications in BlueSpec. Right? So R1 returns the current value if W0 is not enabled, the value being written if W0 is enabled. And similarly, sorry. I can't see myself. All right, good. W1 has higher priority than W0. So this is like the thing, and we can summarize all this in the conflict matrix for this. So I've just, for comparison's sake, drawn first of all the conflict matrix for a register, and when you have EHRs it has many more ports, but if you just focus on port 0, it looks exactly like a register. And now you can tell me what are the properties of port 1 with respect to port 0. So you can see that read ports don't conflict with each other. You can read old value and new value simultaneously, right? So that's conflict free. And similarly, if you are writing something in W0, then that will behave as if it has happened, and you will see R1. So R1 is coming after the right 0 in this. And whenever you have that, then by duality you have the following entries. And now let's look at the entries on W1, right? So W0 comes before W1 because that's how the circuit was in this case. And because if both of them were going in, then W1 will dominate W0. And similarly, you can see that W1 will come after read 1, right? Because that's what you wanted in this case. Sorry, with write 1. W0 comes before that, and in case of read, I'm not showing it here. Right. I think you can fill out all these entries. I mean, you just have to analyze that circuit and you'll be able to figure out what is the conflict matrix. So this is the conflict matrix we're going to assume for our register, for EHRs. Now, let's have fun. So now we have this powerful element EHR, and we can design wonderful things using it. And I'm going to design a variety of FIFOs for you. So here is a pipeline FIFO. An NQ into a full FIFO is permitted provided DQ from a FIFO is done simultaneously. So this is called a pipeline FIFO because it's used in pipelines. Then there is a bypass FIFO. And the bypass FIFO is you can actually DQ from an empty queue provided somebody is NQing at the same time. It just flies through the FIFO, right? So that's a bypass FIFO. And then we'll design a conflict-free FIFO without a dead cycle. So we can do both NQ, DQ simultaneously, as well as, they can't affect each other at all, right? The value of NQ, DQ. So we are not relying on what's happening on NQ in order to enable the DQ. So it's a different property here. Okay, so let's look at this. So this was the FIFO we had, and now I want to turn it into a pipeline FIFO. So what do we want in the pipeline FIFO? That if DQ is happening, then NQ should be allowed. Everybody agrees? That's what the pipeline FIFO is. If DQ is happening, then at the same time I want NQ to go on. All right, so that means DQ is the first thing that you want to do, and this is somehow I have to signal, this V value to the NQ. That's the communication I want in this case, and the way I'm going to do it is I replace this V value with an EHR, right? So it's an EHR. And then what happens here? I write in V0, and the NQ is seeing the bypassed version. NQ is reading the bypass port of this V. It's reading V1 at that point. So effectively, anytime you write here, it's going to see over there. And the effect will be, if this is true, then you will see the NQ will be possible. All right. And what you are reading here is the old value of the valid bit at this point. The moment you replace something by by EHR, then every occurrence of it, you have to attach either a 0 or a 1 to it. Okay. And here NQ will be NQing in V1, which is only visible in the next cycle, because that's the final value that you got over here. So as you can see, the NQ sees DQ, NQ sees DQ. V has the right value in all cases. There is no double write error because writing in different ports is regarded okay, in this case. Not so difficult. So what was the methodology here? Whatever you want to happen first, just assign 0 ports to it. Whosoever wants to see the values, we'll assign ports 1 to it in these EHRs. And that will always work. Let's see here. So So now I want to design a bypass FIFO, and for the bypass FIFO, what do I want to happen first? NQ. If NQ is happening, then I want to fly through, and DQ should be able to see it. So the communication needed is this way, and therefore, I make it again in EHR, and now I say NQ is the first thing, just like before. If there is space, you can NQ it, but now notice I will replace this DQ here with V1. So if somebody was NQing, then DQ will be able to see it, because you're bypassing the value to DQ at that point. And you have to do the same thing with D here, because whatever value NQ is passing, you have to put it out. So D also has to be turned into an EHR. And when you turn D into an EHR, then you wrote D0 over there, and you will see D1 in the first thing over here. Okay, this is saying what I already told you. Okay, good. Now, what was the problem with the 2-element FIFO we had before? So NQ and DQ could go on, but there was a delay in canonicalization. So what I can do is I can assign 0 indices to NQ, DQ first, everything, and then use indices 1 in the canonicalized rule. And that's exactly what I'm going to do. Replace all the registers with EHRs over here. Instead of saying make me a register, you're saying make me an EHR, right? And since NQ and DQ happened first, assign them 0 ports. So that's what I'm doing here. It's pretty mechanical, because it happens first, so you just make all the ports 0 in it. DQ is also happening at the same time, it's conflict free, so everything is zeros. And then when you go and look at the canonicalized rule, everything will become port 1. You will have to look at this code for a few minutes to figure out that I didn't cheat here. But I'm just giving you the mechanical rule. If you have already figured out that you want NQ and DQ to happen before canonicalize, just assign zeros, right? 0 indices to that. And once you do that, it'll do the right thing for you. It'll produce the right circuits for you. In any given cycle, simultaneous NQ and DQ are permitted, provided the FIFO is neither full nor empty, which is the condition you wanted, right, in this case. And there will be no dead cycle in this. Wonderful. I want to talk about one more thing. All right, register files. So we have a register file. What is its property? Right, the property is simply that, just like a register, when you read something from the register file, you see the old values. Whatever you write in the register file will be visible only in the next clock cycle. So the question is, can you design a register file so that you see the writes immediately? You bypass the writes. Anything, if it's coming in, you pass me that and write it also in the register file for future. So that's how a bypass register file works. And if we follow our rule mechanically, I can easily replace this array I had register file with an array of EHRs instead of array of registers. So I can say replicate M, and you have EHRs instead of registers, instead of having registers, and this will easily do the job. A much cleverer idea in this is to do external bypassing. Do I have a picture for that here? Okay, I will show you the picture in a second, but I hope everybody sees that writing the EHR version of this is trivial in this. Okay, so just to summarize this, what's happening, EHRs can be used to design a variety of modules to reduce the conflict between its methods. I've shown you that in 1-element FIFO, NQ, DQ were conflicting, and we can resolve it in 2 different ways, either bypass or as a pipeline FIFO. And this thing you will discover happens in many modules. This way the user of such modules does not have to learn about EHRs. So if you are willing to trust me, say, no, I'm going to give you the right FIFO. You really don't have to know very much about EHRs, because now you will just use the FIFO. Say, what is the right port? Where should I be writing? What do I want? Do I want the bypass value, or do I want the prioritized value, etc., etc. Right? So EHRs were needed in order to design the FIFO, but the use is much easier. Okay. Now remember, in the EHR case, there was a combinational path from input to output which did not exist in a register. So the danger of using EHRs is, and this is not just true for EHRs, this is true for danger of any bypass you introduce in your circuit, is it can increase the combinational delay. It can make the worst path worse, by introducing this delay in that, and therefore it can affect the clock period at which your circuit can run. So we have to be careful. I mean, this is true whenever we introduce bypasses. We have to go and synthesize again and see what happened to my clock period. Did it slow down? Oh, because I get some advantage. I'm communicating faster, but the whole machine may have slowed down, so I may not win, right? So we have to be careful about that. So let me just briefly describe these problems to you, which you will be working in the recitations tomorrow. So this is the one I meant by bypass register file, bypassing done externally. So you have a register file which is normal, just the register file you have been using all the time in the class, and now I package it inside another module, and what I do is I put a FIFO in this module, which is a bypass FIFO. So what will happen now? You enqueue something in it. So instead of writing you write in the register file, all you do is you simply enqueue into this FIFO. And when you read, what do you do? When you read, then you go and search the FIFO. Does anybody have this address I'm looking for? If you find it in the FIFO, you take the oldest value. That is the answer. If you don't, then you'll go and read it from the register file. So that's what your read thing is. And how do values move from bypass FIFO into the register file? At your leisure. Whenever you want, you can copy a value from the bypass FIFO into register file. Has everybody understood what I just said? Right? That I had ordinary register file, I'm writing, but instead of writing directly, I write in a bypass register file. So from outside, I can't tell what is different, because I'm just writing here. But the reader, instead of reading from the register file, it first sees, is there an answer available for me in this bypass FIFO, because that's the one that is most recent, right? So I go and if I find it, I take it, otherwise I take it from the, and remember, by using a bypass FIFO there, I can make it visible immediately. So there is no cheating involved. There is still an EHR, except that making everything an EHR in the register file, I have left the register file alone, and I have just built a tiny FIFO. A little bit of thought will show you one element FIFO is more than enough. So one element bypass FIFO will do the job in this. So that's one code I would like you to write. The other thing I want you to do is analyze this code we had written. Just analyze, when can this rule fire? Under what conditions? What will happen inside this rule? If the valid bit is this, valid bit is that, because it's hard, it's not too difficult to get away, forget about guards which are implicit. But you'll come to appreciate this. You will see that this pipeline behaves almost like the flexible pipeline, like the elastic pipeline we have, right? Because there is so much flexibility you have introduced by having these valid bits, that something can move here, something can move here, which is all allowed in this pipeline. And the third problem is, well, suppose I give you this diagram and I say, sorry, I have only lousy FIFOs. My FIFOs can't do concurrent NQ and DQ. So at that point, you can get depressed. You say, my gosh, there is no parallelism in this. Is that true? Maybe even if you can't do NQs and DQs simultaneously, there is possibility of some parallelism in this. So I want you to think about that. I want you to analyze it.
All right, after you understand all this, we are extremely well poised now to jump into processor pipelines. And we'll be seeing what tricks we can play to make our machine go faster. And you'll be trying out many of those ideas in your project. Very good. Thank you.